There is an object in this universe so massive, so ancient, and so impossibly large that every equation we have says it should not exist. Today we find out what Ton 618 really is, how it broke the rules of the universe, and why 10 billion years later it still matters to you. Now let's begin. Right now, somewhere in this universe, there is an object that could be teleported into the center of our solar system, and you would notice nothing. No explosion, no blinding flash, no shockwave rolling outward through space, just silence, complete, absolute silence. Because Earth, Mars, Jupiter, Saturn, Uranus, Neptune, every planet you've ever learned the name of would already be inside it. Not swallowed in that moment. Already inside. Already gone. Before you had time to blink. That object is called Ton 618. Its event horizon, the boundary beyond which nothing in the universe returns, stretches nearly 400 billion kilometers across. Light traveling at 300,000 kilometers every single second would need more than 15 days to cross from one side to the other. The entire solar system, every orbit, every planet, every moon, every chunk of rock and ice we've ever sent a probe to visit fits inside with room to spare, not a little extra space. The kind of emptiness that makes the whole thing feel even more incomprehensible. And the mass responsible for this 66 billion times the mass of our Sun is not an estimate someone sketched on a napkin. It is a number confirmed through at least 3 entirely independent measurement methods, each one built on different physics, each one arriving at the same staggering conclusion. The universe, it seems, insists on this number being real. But here is the thing. 66 billion solar masses is not the number that should keep you awake at night. The number that matters is 3.3 billion years. That is the age of the universe when Ton 618 already existed at this scale. 3.3 billion years after the Big Bang, when the cosmos was barely a quarter of its current age, when our sun hadn't formed yet, when Earth was not even a thought in the universe's mind. Ton 618 was already there, already enormous, already defying every equation physicists had written to describe how things like it are supposed to come to be. According to every model of astrophysics we currently have that is impossible, the name Ton 618 carries none of the weight of what it describes. It comes from a sky survey catalogue compiled at the Tonantzintla Observatory in Mexico, a dry administrative label assigned the way you'd number a filing box in a storage room, 618. Just another entry in a long list. There is something almost funny about that if you sit with it long enough. The most extreme object ever measured by human science, and it received a name that sounds like a highway exit. When the first signals were picked up in the 1950s and 60s, nobody suspected anything extraordinary. Radio telescopes scanning the sky were finding strange, compact points of emission that didn't match any known star or galaxy. Ton 618 was logged as one of them, a curiosity, a data point, noted and moved past. The moment everything changed came later, when astronomers began measuring the redshift of these objects, a way of reading how much the universe had stretched their light during its long journey to us. When that measurement came back for Ton 618, the number was so far outside the normal range that the research team stopped. They checked the instruments. They ran the calculations again. They rechecked everything. Not because scientists are naturally overcautious, but because accepting the number as simply correct felt harder than assuming something had gone wrong with the equipment. Nothing had gone wrong. Once the redshift was confirmed, the distance snapped into focus. And once the distance was known, the luminosity, the raw energy pouring out of this object every second could be calculated. And once the luminosity was known, the mass required to sustain it without tearing itself apart followed directly from the physics. The answer came back the same way every time, across every method, through every independent line of reasoning, 66 billion times the mass of our Sunday. To feel what that scale actually means, consider this. The black hole sitting at the center of our own Milky Way, Sagittarius A star, the gravitational anchor of the entire galaxy we live in, has a mass of roughly 4 million solar masses. It is by any human measure an incomprehensibly large object, and yet Ton 618 outweighs it by a factor of 16,500. If Sagittarius A star is a pebble you hold in your hand, TON 618 is a 50-story building standing in front of you. Same category of object. A completely different universe of scale. There is a particular kind of silence that follows numbers like these. Not the silence of having nothing to say, but the silence of language running out of road. We have words for large things. We have words for very large things. We do not really have words for this. The mind can point at the number from a distance and recognize that something extraordinary is standing there. That is perhaps the most honest relationship we can have with it. What makes TON 618 feel even stranger is how quietly its discovery unfolded. No dramatic announcement, no singular night of revelation, just data accumulating slowly over decades, each new instrument a little more sensitive than the last, each measurement narrowing the uncertainty until the conclusion became impossible to avoid. Science rarely announces its most astonishing discoveries with fanfare. It tends to whisper them through spectrographs and calibration logs and papers with titles that almost no one outside the field would read twice. And yet here it is, 66 billion solar masses, a region of space that would swallow our entire solar system whole, existing at a point in cosmic history when by every account of how the universe builds things, it had no right to be there yet. What in the universe could create something this large, and why haven't we found anything bigger? But size is not the problem. Size, for all its strangeness, is just a number. The real problem is time. According to modern astrophysics, reaching this mass through the standard processes, the ones written into our best models of how black holes form and grow, would require approximately 50 billion years of continuous feeding. The universe is 13.8 billion years old. TON 618 had already achieved this at 3.3 billion years in. TON 618 didn't just break a record, it broke the schedule of the universe itself. The problem with TON 618 is not that it exists. The universe is large enough and strange enough that most things eventually turn out to be permitted somewhere within its physics. The real problem is the timeline. And when you lay that timeline out, honestly, it stops looking like a puzzle with a missing piece and starts looking like a puzzle where the pieces belong to entirely different boxes. Here is how black holes are supposed to grow. A massive star, something perhaps 30 or 40 times heavier than our sun, burns through its fuel over a few million years, then collapses under its own gravity. What remains is a stellar mass black hole, typically somewhere between a handful and a few dozen solar masses. From there it grows by pulling in surrounding gas, dust, and occasionally other objects that wander too close. This process has a natural speed limit, and physics imposes it firmly. As matter falls inward, it heats up and radiates light. That light pushes outward. At a certain accretion rate, called the Eddington limit, the outward pressure of radiation exactly balances the inward pull of gravity. Try to feed any faster, and the black hole effectively pushes its own food away, working continuously at that maximum rate, starting from a few dozen solar masses and building towards 66 billion. The calculation comes out to roughly 800 million years of non-stop feeding under ideal conditions. And that already assumes a generous starting point. In the early universe at just 3 billion years of age, those ideal conditions didn't exist from the beginning. The universe needed time to cool, to develop structure, to produce the dense concentrations of gas that could serve as fuel in the first place. The timeline has never added up. Scientists have spent decades trying to understand why. 3 serious hypotheses currently compete for the answer, and not one of them fully closes the case. The first is called direct collapse black holes. The idea works like this. In the very early universe, under very specific conditions, intense ultraviolet radiation from nearby young stars, flooding a region of unusually dense primordial gas, a massive cloud of hydrogen and helium, might have been prevented from doing what gas normally does, which is fragment into thousands of smaller clumps that each ignite as separate stars. Instead, the entire cloud could collapse as a single unit, falling directly into a black hole with no stellar phase in between, no stars, no supernovae, just gas becoming gravity all at once, producing an object with hundreds of thousands or even millions of solar masses right from the start. A black hole born that way would arrive at the beginning of cosmic history with a head start that no ordinary stellar remnant could match. From that elevated starting point, standard accretion could plausibly carry it much further within the available time. The physics of direct collapse is not forbidden. The required conditions are simply rare and very specific. The James Webb Space Telescope is currently searching the early universe for objects that might represent exactly this kind of formation. No confirmed detection yet. The search is ongoing. The second hypothesis involves what physicists call super-Eddington accretion, feeding rates that temporarily exceed the theoretical speed limit. The Eddington limit is not an impenetrable wall. It is a balance point. Under the right conditions, if matter pours inward faster than radiation can push it back, the accretion disk can become dense enough to trap its own radiation, and for short bursts, the black hole can grow faster than standard models allow. Computer simulations have shown this is physically plausible. The difficulty is that sustaining such conditions long enough and repeatedly enough to account for something like TON 618 remains extraordinarily challenging to demonstrate even in simulation. The third hypothesis takes a different approach entirely. The early universe was not the orderly, spread-out cosmos we inhabit today. It was denser, more turbulent, more crowded. Galaxies were smaller. The distances between them were shorter. Collisions and mergers were far more frequent than they are now. In that environment, even modest black holes would have encountered each other regularly, merging and combining masses. Every merger releases gravitational waves and adds the combined mass of both objects to the result. A sustained chain of such mergers occurring rapidly in those crowded early conditions could in principle build something very large in a relatively short period of time. Whether it could build something as large as TON 618 as quickly as the timeline demands remains genuinely uncertain. None of these three explanations is fully sufficient. None of them is ruled out. The honest answer, the one most astrophysicists will give when pressed, is that we do not yet know which mechanism or which combination of mechanisms produced TON 618. It remains an open problem, a case with credible suspects and no conviction. And then the James Webb Space Telescope arrived and made everything considerably more complicated. Since beginning scientific operations in 2022, JWST has been returning data from the early universe at a depth and clarity that no previous instrument could approach. What it found there was not what anyone had fully prepared for. Galaxies that are too large and too structured for their age. Black holes that are too massive relative to their host galaxies. Objects appearing too early in numbers, too high at scales that our standard models strain to absorb. The early universe, it turns out, was building things faster and more dramatically than we thought. Not slightly faster, significantly faster. This does not solve the mystery of TON 618. In a real sense, it deepens it, because the anomaly is no longer just one exceptional object that somehow slipped through the rules. It is beginning to look like a pattern. The early universe had a tendency to produce extreme objects on timescales our models were not designed to explain. TON 618 may not be the strange exception. It may be the clearest and most dramatic example of something the universe was doing routinely, something we are only now beginning to see clearly enough to confront. There is a quiet joke that circulates through the astrophysics community, half affectionate, half despairing, that every time JWST transmits a new batch of data from the early universe somewhere, a cosmologist has to sit down and revise their time. Doctoral thesis. The number of dissertations quietly restructured in the telescope's wake is by now considerable. This is not a criticism of those scientists. It is, if anything, a sign that the universe is genuinely more interesting than our most careful guesses about it. If our three best hypotheses still can't fully explain TON 618, is there something fundamental in our understanding of the universe that is wrong? But how TON 618 came to exist is still an open mystery. How it actually works is not. And what it does, the sheer mechanics of its operation, breaks intuition at a level even deeper than its size or its impossible age. TON 618 does not glow. Not a single photon escapes from inside its event horizon. Not one. The darkness at its center is not the darkness of a room with the lights off, or the darkness of a moonless night, or even the darkness of deep space. It is something more absolute than any of those. A region where the geometry of space-time itself prevents light from existing as a thing that moves outward. Whatever falls past that boundary stays there, forever. And yet TON 618 is one of the brightest objects ever detected in the observable universe. That is not a contradiction. It is in fact one of the most precise and revealing things physics has ever shown us. Because what we are seeing when we look at TON 618 has nothing to do with the black hole itself. What we are seeing is matter, enormous quantities of it in the final moments before it disappears. We are watching things die, and in dying at the specific conditions that TON 618 imposes on everything near it, they release energy on a scale that strains the imagination. The structure responsible for this is called an accretion disk. Matter in the vicinity of a black hole does not simply fall straight in the way a dropped object falls toward the floor. It arrives with angular momentum. It is already moving sideways in orbit, the same way planets orbit the sun, rather than spiraling straight into it. As more material accumulates, it forms a flattened, rotating disk around the black hole layer upon layer of gas and dust, all orbiting at different speeds. The inner layers move faster than the outer layers. That difference in speed creates friction. Friction generates heat. And in the environment of TON 618, the heat generated by this process is not the gentle warmth of friction you feel rubbing your hands together. It is hundreds of millions of degrees. At those temperatures, matter no longer exists in any state familiar from everyday experience. It is not gas. It is not liquid. It is not solid. It becomes plasma, the fourth state of matter, in which electrons are stripped entirely from their atoms, leaving behind a seething, electrically charged fluid threaded through with intense magnetic fields. This plasma, compressed and heated to extremes by the relentless inward pull of gravity, radiates energy across every wavelength of light simultaneously. Visible light, ultraviolet, X-rays, radio waves, all of it pouring outward from a disk of dying matter swirling around something that itself emits nothing at all. The numbers that describe this brightness are difficult to place in any familiar context. TON 618's luminosity is estimated at approximately 140 trillion times that of our Sunday. 140 trillion. If you were to place TON 618 at a distance of 50 million light-years from Earth, still farther away than the vast majority of galaxies we consider nearby, it would shine in our night sky with a brightness close to that of a full moon, not as a galaxy, not as a nebula, as a single point of light nearly matching the moon from 50 million light-years away. It is currently 10.4 billion light-years away. That the light we detect from it is measurable at all is a statement about the scale of what is happening there. What makes this even more striking is the efficiency involved. When physicists talk about converting mass into energy, they are referring to the relationship described by Einstein. Mass and energy are interchangeable, and the exchange rate is set by the speed of light squared, which is an enormous number. Most natural processes convert mass into energy with terrible inefficiency. A nuclear fission bomb, the kind that leveled cities in 1945, converts approximately 0.1% of its fuel mass into energy. The sun, through nuclear fusion, at its core converts approximately 0.7%. These are the most energetic processes humans have ever witnessed or created, and they waste more than 99% of the available mass. The accretion process around a black hole can convert up to 40% of infalling mass directly into energy before that mass ever crosses the event horizon. 40%. There is no known natural process in the universe that comes close to this. TON 618 is not merely large, it is the most efficient energy engine that physics permits to exist. And then there are the jets. From the two poles of TON 618, perpendicular to the plane of the accretion disk, matter is being accelerated outward at velocities approaching the speed of light and launched in narrow focused beams into the surrounding space. These jets are not gentle outflows. They extend for tens of thousands of light years in both directions, longer than the distance from our Sun to many of its neighboring stars, stretched across intergalactic space like two enormous, impossibly thin searchlights. The energy they carry is sufficient to affect the formation of stars in galaxies that are not even the same galaxy as TON 618. The jets are powered by the same magnetic fields that thread through the accretion disk wound, and amplified by the rotation of the black hole itself, channeling energy outward even as everything else falls in. TON 618 operates near what is called the Eddington limit, the point at which the outward pressure of all that radiation exactly balances the inward pull of gravity on the infalling material. This is effectively the maximum sustainable feeding rate that physics allows. Exceed it, and the radiation pressure wins, pushing the fuel away and cutting off accretion. Fall too far below it, and the engine dims. TON 618 walks this line, consuming matter at close to the fastest rate the laws of physics will permit, and radiating the consequences of that consumption across 10 billion light-years of space. Why doesn't matter fall straight into the black hole? Why does it form a spinning disk instead? What is stopping it? All of that immense energy, all of that light originates entirely outside the event horizon. Everything we can see, everything we can measure, every photon that has traveled 10.4 billion light-years to reach our instruments was produced in the space surrounding the black hole, not within it. Inside is where light cannot exist as something that moves outward. And when matter finally crosses that boundary, it does not simply vanish. Something far stranger happens to it. Its time vanishes too. In everyday life, time is the thing that keeps everything from happening at once. It flows forward steadily without much drama, and we move through it in the same direction without exception. You cannot step back into yesterday. You cannot slow Tuesday down. Time in ordinary experience is simply the medium in which things occur, transparent, uniform, beyond question. General relativity removes that comfort entirely. According to Einstein's theory, mass does not merely attract other mass. It curves the structure of space-time itself, the four-dimensional fabric in which everything exists and everything happens. And when that fabric curves, time does not flow at the same rate everywhere. In a region with stronger gravity, time runs slower relative to a region with weaker gravity. This is not a metaphor. It is not a philosophical abstraction. It is a measured, confirmed, quantifiable feature of physical reality. The evidence for this is not theoretical. It is running inside your phone right now. The GPS satellites orbiting Earth experience weaker gravity than we do on the surface because they are farther from Earth's center. As a result, their onboard clocks run slightly faster than clocks at ground level by approximately 38 microseconds per day. That gap accumulated over hours would translate into positioning errors of several kilometers per day if the satellites did not continuously correct for it. They do correct for it using the mathematics of general relativity. Every time a GPS system places you on the correct street, it is doing so partly because of Einstein's description of how gravity bends time. That is the effect of Earth's gravity, a gentle, modest, familiar gravity. Near the event horizon of TON 618, the effect is not a matter of microseconds. It is not a rounding error that needs correcting in navigation software. The time dilation near TON 618's event horizon is so extreme that from the perspective of a distant observer, time near that boundary appears to nearly stop altogether. A clock hovering just outside the event horizon would tick so slowly relative to a clock far away that the difference would not be described in microseconds or minutes or years. The gap becomes effectively unbridgeable. This leads to one of the most disorienting results in all of physics, the observer paradox surrounding black holes. Imagine watching someone fall toward TON 618 from a safe distance. As they approach the event horizon, you would see them slow down. Their movement would become more and more sluggish. The light reaching you from them would shift toward longer wavelengths, growing redder and dimmer, and then they would appear to freeze. Not stop moving and hover, but genuinely freeze in place, suspended at the threshold, growing dimmer until they fade entirely from view. From your vantage point, they never cross. They approach forever. Now consider the experience of the person falling. From their own perspective, nothing unusual happens at the moment of crossing. No jolt, no wall, no sudden alarm. The event horizon is not a physical surface, there is nothing there to collide with. They simply fall freely through a mathematical boundary and continue inward. They cross in finite time without fanfare and proceed toward the interior. Both of these descriptions are correct. They are not two versions of the same event, where one is wrong and one is right. They are two genuinely different, but equally valid realities, each true within its own frame of reference. This is not a paradox that physics needs to resolve. It is a feature of how space-time actually works, when mass becomes extreme enough. Space-time is not a single shared stage on which everyone watches the same performance. It is something that bends, and what you see depends entirely on where you are standing within it. TON 618 adds further layers to this strangeness through its rotation. A spinning black hole in TON 618 almost certainly spins does not merely curve space-time around it. It drags space-time around with it the way a spinning ball dragged through honey pulls the honey into rotation. This effect is called frame dragging. Near TON 618, even empty space is not still. The vacuum itself is being pulled into rotation. In the region just outside the event horizon called the ergosphere, nothing can remain stationary relative to the distant universe. Not particles, not photons, not anything. Everything is forced to orbit not by choice, not by momentum, but simply by the geometry of what spinning mass does to the space around it. And then there is what TON 618 does to light that doesn't fall, in light that merely passes nearby. The curvature of space-time around it bends the paths of photons traveling from distant galaxies behind it, warping them into arcs and rings. When the alignment is precise enough, a galaxy directly behind TON 618 would appear to us not as a point or a smear, but as a complete, perfect ring of light. Encircling it, an Einstein ring, a natural magnifying lens created by gravity alone. Astronomers use these gravitational lenses, deliberately pointing their telescopes at massive objects like TON 618, specifically to observe things that would otherwise be too faint and too distant to see. The black hole in this context becomes a tool. The most extreme distortion of space-time becomes, in practice, the universe's own optical instrument. If two observers watch the same event from two different positions in a strong gravitational field, and both see genuinely different things, where does the truth lie? Outside the event horizon, physics still functions strangely beautifully at its absolute limits, but it functions. But the moment something crosses that boundary, one of the two most fundamental things in the universe, space and time, trade places with each other. And no equation we have can follow all the way to the end. Step outside on a clear night and look up. Every direction you can choose to walk, north, south, east, west, forward, backward, remains genuinely open to you. You can change your mind mid-step. You can turn around. The future contains options, and space in every direction you can point is something you can move through or away from freely. This feels so natural, so obvious, that it barely registers as a feature of reality. It simply is reality. Cross the event horizon of TON 618, and that changes. Not gradually, not partially, completely. Inside the event horizon, the roles of space and time exchange places with each other. Outside, you move through space freely and are carried through time in one direction. Whether you want to be or not, you cannot stop aging, cannot reverse the clock. Inside, that logic inverts. Time, in a sense, becomes the dimension you can move through freely, or rather the dimension that physics allows to still vary. Space, on the other hand, collapses into a single direction. Every path through space, regardless of which way you point, leads to the same destination. There is no left or right or up or down in any meaningful sense. There is only inward. The singularity is not somewhere you might end up. It is somewhere every possible direction leads. You cannot avoid it any more than you can avoid the next second of time while sitting in your chair. There is no choice. There is no turning back. The geometry of space-time inside the event horizon makes return not merely difficult or physically demanding, it makes it as meaningless as asking why you can't walk back into yesterday. Now, consider what happens to matter on the way there. And this is where TON 618 reveals something that in its own way is more unsettling than a violent death. With a small black hole, one with a mass of a few dozen or a few hundred solar masses, the gravitational difference between one side of a falling object and the other is enormous, even at the event horizon. Gravity pulls harder on the near side than on the far side. This difference in pull, called a tidal force, stretches the object along the direction of fall and compresses it sideways. The result carried to its extreme is what physicists call spaghettification. The object is drawn out into a long, thin strand of matter before it ever reaches the boundary. Death in this context is at least immediate. Violent, certainly, but immediate. TON 618 is different. Because its event horizon is so enormously large, nearly 400 billion kilometers across, the gravitational difference between one side of a falling object and the other, at the moment of crossing that boundary, is actually quite small. The tidal forces at the event horizon of TON 618 are gentle enough that a human body or a spacecraft could cross the threshold entirely intact without feeling anything unusual in that moment. No alarm. No physical sensation marking the transition. Just an invisible line crossed in silence, after which every direction in space points toward the same inevitable end. There is something distinctly more disturbing about that than instant destruction. At least with a small black hole, the boundary announces itself. TON 618 offers you a quiet crossing, and only afterward, as you move deeper and the tidal forces grow, does the end become physically apparent. You would cross into the unreturnable, not knowing you had crossed. At the mathematical center of all of this sits what physics calls the singularity. This is the point in the equations of general relativity where density becomes infinite and the curvature of space-time becomes infinite. And it is important to understand what infinity means in this context, because it does not mean very large. It does not mean larger than we can currently measure. Infinity in a physical equation means the equation has failed. It means the mathematical model that describes reality everywhere else has reached a point where it no longer describes anything real. The map has run out of territory. The model has collapsed under its own demands. Whatever actually exists at the center of TON 618, and something must exist there because matter falls in and has to go somewhere, our current physics cannot describe it. General relativity, the most precisely tested theory of gravity in the history of science, produces a nonsense answer at that point and stops. This is not a gap in our data. It is a gap in our framework. The singularity is where our best description of reality formally admits it does not know what it is talking about. This collision between what we know and what we cannot reach becomes most acute in what physicists call the information paradox. Quantum mechanics, the other great pillar of modern physics governing the behavior of particles at the smallest scales, contains a principle that is foundational to everything. The theory predicts information about the physical state of any system is never destroyed. It may become scrambled, redistributed, encoded in forms that are practically impossible to read, but it cannot simply cease to exist. The total information content of the universe is conserved always. Black holes appear to violate this directly. Matter falls in, carrying with it information about its state, the positions of its particles, their velocities, their quantum properties. Once inside the event horizon, that information cannot get out. If the black hole eventually loses mass and disappears through Hawking radiation, where does the information go? These two complete, independently verified theories of physics give contradictory answers. Quantum mechanics says the information must survive. General relativity applied to black holes says there is no way out. Both theories are right in every context where they can be tested. Inside a black hole, they disagree. This is the information paradox, and it remains one of the most unresolved problems in all of theoretical physics. In 1974, Stephen Hawking demonstrated theoretically that black holes are not perfectly black. Quantum effects near the event horizon cause pairs of particles to spontaneously appear, one falling inward, one escaping outward as radiation. Over vast timescales, this process slowly drains the black hole's mass. For a black hole the size of TON 618, the timescale involved is not merely long. It is a number so large it cannot be meaningfully communicated in ordinary language. Written out, it would be a 1 followed by 100 zeros, years. The current age of the universe is roughly 14 billion years, which is a 14 followed by 9 zeros. The gap between those two numbers is not a matter of degree, it is a matter of kind. And yet, even across that incomprehensible span of time, the paradox remains. Does the slowly escaping Hawking radiation carry the information back out encoded in correlations too subtle to detect? Or is the information genuinely lost? Hawking himself changed his position on this question more than once over the course of his career. One of the most serious attempts to resolve this is called the holographic principle. The idea, which emerged from work in string theory and quantum gravity in the 1990s and continues to be actively developed, proposes that all the information about everything that has ever fallen into a black hole is encoded on the surface of the event horizon itself, a two-dimensional surface containing a complete description of the three-dimensional interior, not as a metaphor, as a literal statement about how information is stored in space-time. If this principle is correct, then the event horizon of TON 618, that surface nearly 400 billion kilometers across, is the largest information storage structure in the known universe. Every particle that has ever fallen in every atom, every quantum state, every fragment of the history of 66 billion solar masses of accumulated matter, encoded on a surface that emits no light and reveals nothing to any telescope, we possess. If information cannot be destroyed but also cannot escape from a black hole, where does it go? TON 618 is the limit of modern physics. But the light that left it 10 billion years ago carries more than the mysteries of a black hole. It carries the entire history of a universe we barely recognize. There is something quietly strange at the heart of every astronomical observation ever made. Something so fundamental that it tends to slip past without examination. When you look at a star, you are not seeing it as it is. You are seeing it as it was, the light that left it years, decades, centuries ago, arriving now carrying an image of a moment already gone. The farther away the object, the older the image. And for something as distant as TON 618, the image is not centuries old or millions of years old. It is 10.4 billion years old. But here is where it gets genuinely strange. From the perspective of the photon itself, the individual particle of light that traveled from TON 618 to the detector of a telescope on Earth, none of that time passed at all. This is not a poetic way of describing a long journey. It is a direct consequence of special relativity. A photon travels at the speed of light, and at the speed of light, time dilation becomes total. For the photon, the moment it was emitted at the edge of TON 618's accretion disk and the moment it struck a mirror in a telescope on Earth are not separated by 10 billion years. They are the same moment. There is no elapsed time between them, no experience of travel, no aging, no distance crossed in any felt sense. The photon does not experience a journey, it simply ceases to exist at one location and comes into existence at another with no interval between. What this means for the observation is remarkable. We are not seeing TON 618 as it roughly was, with some information lost along the way, degraded by distance and time like a photocopy of a photocopy. We are seeing it with perfect fidelity, the exact state of its accretion disk, its temperature, its chemical composition, its velocity structure, at the precise moment that light was emitted. The photon is a perfect record. It carries no distortion introduced by the journey, because from its perspective, there was no journey. The universe changed around it. The photon itself did not. What did change significantly is the wavelength of that light. When the light left TON 618, the space between that point and the Milky Way was far smaller than it is today. The universe has been expanding continuously since the Big Bang, and in the 10.4 billion years since that light was emitted, the space through which it traveled stretched enormously. This stretching pulled the light's wavelength along with it, the way a wave drawn on a rubber band stretches when you pull the band. The ultraviolet radiation that originally poured from TON 618's blazing accretion disk arrived at Earth, shifted so far toward longer wavelengths that much of it is now detectable in infrared and radio frequencies. The light we measure is the same light carrying the same information, but written in a different language than the one it started in. This stretching is described by what astronomers call the redshift value, written as Z equals 2.219 for TON 618. A redshift of 2.219 means that the universe has expanded by a factor of more than 3 since that light was emitted. Every wavelength of every photon from TON 618 has been stretched to more than 3 times its original length during transit. From this redshift, 2 different distances can be derived, and they tell very different stories. The look-back time distance, the length of time the light spent traveling, is 10.4 billion light-years. That is the age of the image we are seeing. But the actual current position of TON 618, accounting for the expansion of space that has occurred since the light left, is approximately 17 billion light-years away from us today. These are not the same number, and the difference matters enormously. For one specific reason, 17 billion light-years places TON 618 beyond any possibility of contact ever. Not merely impractical contact, geometrically impossible contact. The space between us is expanding faster than light could cross it. Whatever TON 618 is today, if it still exists in any recognizable form, we will never know. No signal we send will reach it. No signal it sends now will reach us. The 17 billion light-year version of TON 618 is permanently, irreversibly beyond our horizon. What we have is the 10.4 billion-year-old portrait, and even that portrait contains more information than it might appear to hold. On its way from TON 618 to Earth, that light did not travel through empty space. It passed through hundreds of intervening clouds of hydrogen gas distributed across the vast stretches of intergalactic space. Each cloud left its mark. Hydrogen absorbs light at very specific wavelengths, and each time the light from TON 618 passed through one of these clouds, a thin slice of its spectrum was absorbed and removed, leaving a dark line. Hundreds of clouds produced. Hundreds of lines stacked across the spectrum, like the marks of everything the light had passed through on its journey. Astronomers call this the Lyman alpha forest, a dense thicket of absorption lines in the spectrum of distant quasars, each line corresponding to a different cloud of gas at a different distance, at a different point in cosmic history. Reading this forest is like reading the growth rings of a tree, each layer recording the conditions of a specific moment in time. From the pattern of lines in TON 618 spectrum, astronomers can reconstruct the distribution of ordinary matter along 10.4 billion light-years of cosmic space mapping. How gas has clustered and thinned across the history of the universe. The light from TON 618 did not merely travel through space. It sampled it, recorded it, and delivered that record to us intact. If a photon does not experience time, then the 10 billion-year journey belongs to whose experience? The map of matter that the light from TON 618 carries does not only show what lies between here and there, it reveals the hand of something invisible that has been directing the entire structure of the universe all along. Take everything you have ever seen, everything that has ever been observed, measured, detected, or inferred through any instrument ever built, every star in every galaxy, every cloud of gas and dust, every planet, every asteroid, every atom of ordinary matter that makes up the visible universe, and add it all together. That total accounts for approximately 5% of everything that exists. The other 95% is something else entirely. This is not a provisional number pending better measurements. It is one of the most precisely established and repeatedly confirmed results in modern cosmology. The universe we can see, touch, and measure in any conventional sense, the universe of chemistry and light and nuclear physics, is a thin residue floating on top of a much larger reality that operates by different rules, or at least rules we haven't yet managed to identify. 27% of the total mass energy content of the universe is dark matter. It does not emit light. It does not reflect light. It does not absorb light in any way that any instrument has yet detected. It passes through ordinary matter without interaction, as if ordinary matter barely exists from its perspective. You cannot see it, not because it is hidden or distant, but because it simply does not engage with the electromagnetic spectrum at all. The only way we know it is through gravity, the way it pulls on things. We can see bending their paths, altering their speeds, clustering them in ways that cannot be explained by the visible matter alone. The evidence for this is not subtle. Consider the rotation of galaxies. In a galaxy held together only by the gravity of its visible stars and gas, objects at the outer edges should orbit more slowly than objects near the center, the same way the outer planets of our solar system orbit more slowly than the inner. Honest. This is straightforward gravitational physics, and it works perfectly at the scale of planetary systems. But when astronomers measure the rotation speeds of stars at the outer edges of large spiral galaxies, they find something completely different. Those stars are moving far too fast. If only the visible mass were present, the gravity would be insufficient to keep them in orbit. They would fly off into intergalactic space. They don't. Something is holding them. Something with mass, substantial mass, distributed in an extended halo around and beyond the visible galaxy, is providing the additional gravity needed to keep everything bound together. That something is dark matter. The largest structure in the universe, what cosmologists call the cosmic web, traces the distribution of dark matter with extraordinary fidelity. The cosmic web is a network of vast filaments, strands of matter, hundreds of millions of light-years long, connecting nodes where filaments intersect. Between the filaments lie enormous voids, regions of space nearly empty of galaxies, stretching across hundreds of millions of light-years. Galaxies form and cluster along the filaments. The densest nodes, where multiple filaments meet, host the largest galaxy clusters in the universe. And the entire architecture of this web, the pattern of filaments, nodes, and voids, matches the distribution of dark matter with a precision that no model based on ordinary matter alone can reproduce. Dark matter is the skeleton. Everything we can see is built on top of it. TON 618 formed at one of the densest intersections of this web in the early universe, a point where multiple dark matter filaments converged, funneling gas inward at rates and concentrations that would have been impossible in a less extreme location. The extraordinary density of that environment is part of what allowed something as massive as TON 618 to accumulate so much material so quickly. Without dark matter establishing the scaffolding of those filaments, the conditions that produce TON 618 would likely never have existed. Then there is the remaining 68%. This is dark energy, and it is different in kind from dark matter, not merely in detectability. Dark matter has mass, it clusters, it responds to and generates gravity. Dark energy is not matter at all. It appears to be a property of space itself, an energy inherent to the vacuum, present everywhere uniformly, not clustering or concentrating, but causing the expansion of the universe to accelerate. Every second, the space between galaxy clusters grows slightly larger, and dark energy is what drives that growth. Its effect is the opposite of gravity at the largest scales, not pulling things together but pushing them apart at an accelerating rate that means the most distant galaxies are receding from us faster than light. No one knows what dark energy is. There is no satisfying theoretical explanation for why empty space should carry energy, or why that energy should have exactly the value it does. It was discovered in 1998 when two independent teams studying distant supernovae found that the expansion of the universe is not slowing down under gravity. As expected, it is speeding up. Both teams arrived at the same conclusion independently, and both were awarded the Nobel Prize in Physics in 2011 for the discovery. The result has been confirmed by multiple independent methods since. Dark energy is real. What it is remains entirely open. So, to summarize the current state of human knowledge about the contents of the universe, 5% is the matter we understand, 27% is matter we know exists, but cannot directly observe or identify, and 68% is an accelerating expansion driven by something we cannot explain inherent to the vacuum with no agreed theoretical basis. After thousands of years of astronomy, the honest accounting of what the universe is made of looks something like this, and it is in its way more astonishing than any single object within it. If 95% of the universe is something that science does not yet truly understand, what does that change about the meaning of the phrase, "we understand the universe"? Dark matter built the skeleton of the universe. But what breathed life into that skeleton, what ignited TON 618 and millions of quasars like it, was a period of cosmic history that we are only now beginning to understand. To understand what TON 618 lit up, you first have to understand what it lit up into. And that requires going back further back than galaxies, further back than stars, to a time when the universe was a fundamentally different kind of place. Approximately 380,000 years after the Big Bang, the universe had expanded and cooled enough for a specific transition to occur. Before that moment, the universe was so hot that electrons could not remain attached to protons. Any atom that tried to form was immediately torn apart by the surrounding radiation. The entire cosmos was a dense, opaque plasma, so thoroughly tangled with light that photons could not travel more than a short distance before colliding with a free electron and scattering in a new direction. The universe was bright in a physical sense, filled with radiation. But that radiation was trapped, unable to move freely, unable to carry any image or information across any meaningful distance. Then the temperature dropped past a threshold. Electrons and protons combined into neutral hydrogen atoms for the first time and held together. The fog lifted. Light, suddenly freed from the constant collisions that had confined it, streamed outward in all directions across the newly transparent universe. That release of light is what we detect today as the cosmic microwave background radiation, the oldest light in the universe. A faint glow of microwave radiation reaching us from every direction in the sky, carrying the imprint of what the universe looked like at that earliest moment of transparency. It is a photograph of the universe at 380,000 years of age. But the clarity did not last. After that first release of light, the universe entered a period that cosmologists call the cosmic dark ages. There were no stars yet, there were no galaxies, there was no source of new light anywhere. The hydrogen that had just formed into atoms drifted in vast, cold, dark clouds through an expanding universe that contained no illumination at all. For hundreds of millions of years, the estimates range from roughly 200 million to perhaps 800 million years after the Big Bang. The universe was genuinely, completely dark. Not dark the way a room is dark when the lights go out. Dark the way existence is dark when there is nothing capable of producing light anywhere within it. What ended the Dark Ages was the ignition of the first stars, and shortly after the first quasars, as the densest regions of dark matter drew hydrogen gas inward and the first massive stars began to burn. They emitted ultraviolet radiation, high-energy light, capable of stripping electrons back off the hydrogen atoms that had formed hundreds of millions of years earlier. Wherever a star or a quasar ignited, a bubble of ionized transparent gas expanded outward around it. At first, these bubbles were isolated, separated by vast stretches of still neutral, still opaque hydrogen. But as more sources lit up and the bubbles grew, they began to overlap. Slowly then, more rapidly, the neutral hydrogen was cleared away and the universe became transparent to ultraviolet light, not just in patches, but everywhere. This process is called reionization, and it represents the moment the universe transitioned into the form we recognize today. TON 618 and the quasars of its era were among the primary agents of this transformation. A quasar pouring out radiation equivalent to hundreds of trillions of solar luminosities does not merely illuminate its immediate surroundings. It ionizes vast regions of surrounding intergalactic gas, carving out bubbles of transparency that extend for millions of light years in every direction. The most powerful quasars of the early universe were not passive lights in a dark room. They were actively rewriting the physical state of the gas that filled the space between galaxies. Without them, reionization would have taken longer or proceeded differently, or perhaps not completed at all within the time frame that allowed subsequent structure to form as it did. Before reionization, the universe was effectively opaque to ultraviolet light, like trying to see through a dense, featureless fog. After reionization, the fog cleared, and for the first time, galaxies on opposite sides of the universe could in principle see each other. The universe became the luminous, structured place that our telescopes now map. Every observation we make of a galaxy, every image of a distant quasar, every spectrum of a star cluster is only possible because reionization happened, because objects like TON 618 burned bright enough and long enough to complete the job. The period when TON 618 was active also coincides with the peak of star formation in the universe's history. The rate at which new stars formed across all galaxies combined was 10 to 30 times higher during that era than it is today. The universe was converting gas into stars at a pace it has never matched since and will never match again. Quasars, galactic collisions, and intense star formation were not separate phenomena happening in parallel, they were expressions of the same underlying condition. The early universe had abundant gas, high densities, frequent mergers, and active black holes, all feeding into one another, producing an era of construction that lasted a few billion years and then gradually wound down. The James Webb Space Telescope is now looking directly into this period and earlier, capturing light from galaxies that formed within the first few 100 million years after the Big Bang. What it is finding consistently challenges the expected timeline. Galaxies appear more massive, more structured, and forming stars more vigorously than models predict for their age. Reionization itself may have begun earlier than previously thought. Each new dataset adjusts the picture, and the adjustments consistently point in the same direction. The early universe was more active, more organized, and more extreme than our models had room for. If the universe spent hundreds of millions of years in complete darkness before the first light appeared, how did that first light emerge in a universe with nothing yet capable of burning quasars, like TON 618, lit up the universe and shaped it into what we see today, including the Milky Way? And the Milky Way carries hidden evidence that it was once one of them. At the center of the Milky Way, approximately 26,000 light-years from Earth, sits a black hole called Sagittarius A star. It has a mass of roughly 4 million solar masses, enormous by any ordinary measure, the gravitational anchor of an entire galaxy of hundreds of billions of stars. And right now it is doing almost nothing. It is consuming matter at a rate so low that by the standards of active black holes it is essentially dormant, quiet, patient. To all appearances at rest. But it has not always been quiet, and the evidence of what it once did is written across the sky in structures so large they took decades to notice. In 2010, NASA's Fermi Gamma Ray Space Telescope detected something unexpected, extending above and below the plane of the Milky Way. Two enormous lobes of hot gas and high-energy radiation, one billowing upward from the galactic center, and one extending downward, each stretching approximately 25,000 light-years from the midplane. These structures, now called the Fermi bubbles, are not subtle features at the edge of detectability. They are among the largest coherent structures in the Milky Way, and they cannot be explained by any normal process of stellar activity or gradual gas flow. The energy required to produce them, the sheer quantity of radiation and high-energy particles necessary to inflate two bubbles of that size, points to a single explanation: a massive outburst from Sagittarius A star itself, occurring somewhere between a few million and perhaps 20 million years ago. In that event, Sagittarius A star released energy at a rate far exceeding anything it produces today, driving material outward at high velocity and carving these enormous cavities into the gas surrounding the galactic center. The Fermi bubbles are a scar, a record of violence preserved in the structure of the galaxy from an era when the sleeper at the Milky Way's heart was briefly awake. The other evidence for Sagittarius A star's existence and nature comes not from what it has done to the surrounding galaxy, but from the stars that orbit it directly. A cluster of stars, known as the stars, occupies the region within a fraction of a light-year of the galactic center. These stars move in ways that defy any simple explanation. The fastest among them have been measured, traveling at speeds reaching approximately 3% of the speed of light, making them the fastest moving stars ever directly observed. Their orbits are tight ellipses that swing them extremely close to the galactic center and then fling them back out. For any object to maintain such an orbit without being disrupted, the mass at the center it orbits must be extraordinarily concentrated. The star's behavior is consistent with one explanation: only a black hole of approximately 4 million solar masses, occupying a region of space smaller than our solar system. Tracking those orbits required decades of patient observation. Reinhard Genzel and Andrea Ghez led two independent research teams that spent more than 25 years monitoring the stars, mapping their paths with increasing precision as telescopes improved. In 2020, the Nobel Prize in Physics was awarded to both of them, along with Roger Penrose, for separate theoretical work on black holes in recognition of this achievement. The prize was, in effect, a formal acknowledgement by the scientific community that the case for Sagittarius A star was not merely compelling, but proven. Then in 2022, the Event Horizon Telescope collaboration published the first direct image of Sagittarius A star itself. The Event Horizon Telescope is not a single instrument. It is a planet-spanning network of radio observatories that function together as a single telescope with an effective diameter equal to the diameter of Earth, achieving the telescope resolution necessary to image the immediate surroundings of a black hole. The image showed exactly what general relativity predicted: a bright ring of light formed by photons orbiting the black hole before spiraling inwards, surrounding a dark central region, the shadow of the event horizon. It matched the theoretical predictions with a precision that left no room for alternative interpretations. The same collaboration had produced a similar image of the black hole at the center of the galaxy Messier 87 in 2019. These two images together represent the closest humanity has come to directly confronting the object at the heart of the physics of gravity. But Sagittarius A star, as it exists today, quiet, barely fed, leaving only ancient scars as testimony to its more active past, is not the permanent state of the Milky Way's center. It is a temporary one. In approximately 4.5 billion years, the Milky Way will collide with the Andromeda Galaxy, our nearest large galactic neighbor. This event has been known for years and is confirmed by measurements of Andromeda's trajectory toward us. When the collision occurs, and it will be a slow, complex merger lasting hundreds of millions of years rather than a sudden impact, it will funnel enormous quantities of gas toward the centers of both galaxies. That gas will reach Sagittarius A star. Fed with fresh material on a scale it has not experienced in billions of years, it will awaken. The accretion disk will reform. The jets will ignite. From a sufficient distance, an observer watching the merged galaxy, sometimes called Milkdromeda, would see at its heart something resembling what we see when we look at TON 618 today. A quasar, a blazing center, the Milky Way briefly wearing the same face that TON 618 wore 10 billion years ago. When Sagittarius A star reactivates and the Milky Way becomes a quasar, what happens to the planetary systems within the Milky Way, including our own solar system? The Milky Way was once a quasar. Sagittarius A star may become one again. And the atoms that make up everything we are have traveled through the entirety of that journey, from primordial gas clouds, through stellar cores, through supernova explosions, to here, not as metaphor, as physical fact. When the Big Bang occurred, it produced a universe of extraordinary simplicity. The matter that emerged from those first minutes of existence was almost entirely hydrogen, approximately 75%, and helium, approximately 25%, with trace amounts of lithium scattered through the rest. That was the complete inventory. The entire periodic table as we know it today, with its 92 naturally occurring elements and the extraordinary chemistry they make possible, did not yet exist. The universe in its earliest form was chemically almost bare. Every element heavier than those first three, the carbon that forms the backbone of every living molecule, the oxygen bound into every breath, the iron carried in every red blood cell, the calcium laid down in every bone, was made somewhere else, at some later time inside something that did not yet exist. When the Big Bang occurred, it was made inside stars. The process begins with gravity. A cloud of hydrogen gas, dense enough and cold enough, begins to collapse under its own weight. As it compresses, the temperature at the center rises. When it reaches approximately 10 million degrees, hydrogen nuclei protons begin moving fast enough to overcome their mutual electrical repulsion and collide with sufficient force to fuse together. Nuclear fusion ignites. The star is born. And from that point forward, the star is engaged in a long, slow act of elemental construction, building heavier nuclei from lighter ones, releasing energy at each step that holds the star against further collapse. Hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. Carbon and oxygen fuse into neon, magnesium, silicon, sulfur, and a cascade of heavier elements through successive burning stages, each one occurring at higher temperatures and shorter timescales than the last. The sequence ends at iron. Iron is where nuclear fusion stops releasing energy and starts consuming it. When an iron core accumulates at the center of a massive star, fusion can no longer support the star against gravity. The core collapses in less than a second. The outer layers, falling inward and then rebounding from the suddenly rigid core, are expelled outward in the most energetic explosion in the observable universe, a supernova. In the few seconds of a supernova explosion, the energy released exceeds what our entire galaxy produces over several months. Within that brief, violent event, the extreme conditions of temperature and neutron density create element that no stellar burning stage can produce: gold, uranium, iodine, platinum, and dozens of others heavier than iron forged in the chaos of Karnstar. The explosion itself, or in the collision of neutron stars that supernovae sometimes leave behind. These elements are scattered outward into interstellar space, along with everything the star had been building across its entire lifetime. The first generation of stars formed from the pure hydrogen and helium of the early universe. They lived fast. The most massive among them burned through their fuel in a few million years, and they died in supernovae that seeded the surrounding space with the first heavy elements the universe had ever contained. Those elements drifted, cooled, mixed with fresh hydrogen in the interstellar medium, and gradually concentrated into new clouds. Those clouds collapsed into new stars, second-generation stars, chemically richer than the first. Some of those stars also lived and died, adding their own processed material to the interstellar mix. The cycle repeated each generation, building on the chemical inheritance of the one before. The first generation of massive stars lived and died during the same cosmic era that TON 618 dominated. While TON 618's accretion disk blazed and its jets carved through intergalactic gas, the earlier supernovae were scattering the first heavy elements across their host galaxies. That material, carbon, oxygen, silicon, iron, dispersed through the interstellar medium, cooling across hundreds of millions of years, mixing and accumulating across billions more, until approximately 4.6 billion years ago, a particular present place, cloud of enriched gas in an unremarkable spiral galaxy, collapsed and ignited as the sun, leaving the remaining material to coalesce into the planets of our solar system. The atoms in your body are specific physical objects with a history. The carbon in your DNA was fused in the core of a star that died before the sun existed. The oxygen in your lungs passed through at least one supernova before reaching this planet. The iron in your blood was forged in a stellar interior, expelled in an explosion, drifted through interstellar space, incorporated into the solar nebula, accreted into Earth, cycled through geological processes, entered the biosphere and exhalations, arrived eventually in you. This is not an approximation or a poetic compression of a more complicated truth. It is the actual sequence of events reconstructed from nuclear physics, stellar evolution models, and isotopic measurements in meteorites and planetary rocks. The atoms in your body are old in a way that the word old cannot contain. They have been part of stars. They have been part of explosions. They have been part of interstellar clouds drifting in darkness for millions of years. The cycle of matter has no beginning and no endpoint, only continuous transformation. Black holes are a node in that cycle too. Matter falls in and energy pours out in radiation and jets. That energy heats and compresses surrounding gas clouds, sometimes triggering the collapse that forms new stars. The destruction at the center drives creation at the periphery. What Ton 618 consumed fed its jets, and its jets may have compressed gas clouds that eventually became stars, some of which eventually became supernovae, some of whose material eventually drifted far enough and long enough to become, among countless other things, part of us. There is no clean line between what Ton 618 is and what we are. The universe does not draw those lines. Matter moves, transforms, and continues. Always the same atoms, always different arrangements, always part of the same unbroken chain of physical consequence, stretching from the earliest moments after the Big Bang to right now. If the atoms in your body were once part of multiple different stars, before they were part of you, where do you begin and where do you end? We are not merely made from the ash of dead stars. We are the part of the universe that is looking at itself. And that act of looking is breaking things we thought were the foundations of science. Something unusual is happening in cosmology at this precise moment in history. It is not the usual pace of science, the slow accumulation of data, the gradual refinement of models, the incremental narrowing of uncertainty. What is happening now is faster and more disruptive than that. Within the span of a few years, multiple independent lines of observation have converged on a set of results that do not fit comfortably within the standard model of cosmology. The framework that has successfully described the prophet, large-scale structure, and evolution of the universe for decades. The cracks are not small, and they are not going away. The James Webb Space Telescope was launched in December 2021 and began science operations in 2022. It was designed to see further back in cosmic time than any previous observatory, observing in infrared wavelengths that allow it to detect light from the earliest galaxies, light so redshifted by cosmic expansion that it is invisible to optical telescopes. What it found in its first years of operation was not what the models predicted. Galaxies appeared in the early universe within the first few 100 million years after the Big Bang that are too massive, too structured, and too bright for their age. Some of them contain stellar populations that, based on their colors and spectra, appear to have been forming stars vigorously for hundreds of millions of years, before the point at which they are observed, which would push the onset of their star formation back to a time when, according to standard models, the conditions for galaxy formation had barely begun to develop. Supermassive black holes appeared at redshifts corresponding to times less than 1 billion years after the Big Bang at masses that the standard growth models struggle to account for. Some of these objects appear to be more massive relative to their host galaxies than the well-established correlation between black hole mass and galaxy mass would predict, suggesting that in the early universe, black holes may have grown faster than their galaxies, reversing the relationship seen in the local universe. A number of cosmologists have used the phrase early universe crisis to describe the accumulating tension between JWST's observations and standard predictions. This is not a casual expression. The data has been checked, rechecked, and confirmed across multiple independent teams working on different objects and different methods. The discrepancies are real and consistent. Whether they represent a need for modifications to existing models within the current framework or something more fundamental remains actively debated. Simultaneously, a separate tension has been building around a number called the Hubble constant, the value that describes the current rate of expansion of the universe. Two entirely independent methods of measuring this number give results that disagree by approximately 8 to 9%. One method measures the expansion rate using the cosmic microwave background radiation and extrapolates forward through time using the standard cosmological model. The other uses direct measurements of distances and velocities of nearby galaxies, calibrated through a chain of standard candles including pulsating stars called Cepheids and Type Ia supernovae. Both methods are well established, independently validated, and internally consistent. They simply do not agree with each other. The statistical confidence of the disagreement has now reached a level that rules out random measurement error. Something is producing this discrepancy, and the most interesting possibility is that it reflects new physics, not captured by the current model. While these tensions have been developing in the domain of light-based astronomy, an entirely new observational window has opened. In 2015, the LIGO collaboration detected gravitational waves for the first time, ripples in the fabric of space-time produced by the merger of two black holes, approximately 1.3 billion light-years away. The detection lasted less than a second and carried information about an event that released more energy than the Sun will emit across its entire 10 billion-year lifetime. Gravitational waves are not light. They are not affected by gas, dust, magnetic fields, or anything that obscures or distorts electromagnetic radiation. They pass through the universe essentially unchanged, carrying direct information about the motion of mass in some of the most extreme environments physics permits. They are, in the most literal sense, a new sense, astronomy's first ear, as distinct from its existing eyes. LISA, the Laser Interferometer Space Antenna, is a gravitational wave observatory planned for launch in 2037. Unlike LIGO, which is ground-based and sensitive to relatively high-frequency gravitational waves from stellar mass black hole mergers, LISA will operate in space and will be sensitive to much lower frequencies, the frequencies produced by the mergers of supermassive black holes objects, in the mass range of millions to billions of solar masses. TON 618 and its contemporaries, if they underwent mergers during the early universe, would have produced gravitational waves in exactly this frequency range. LISA's sensitivity will extend to distances and epochs comparable to where and when TON 618 existed. For the first time, we will be able to detect the space-time ripples produced by events at cosmological distances, not just see them in light, but feel them in the geometry of space itself. In 2023, this new capability produced its first major result, though not from a space-based detector. Multiple, independent research teams around the world, using networks of pulsars as natural gravitational wave detectors, an approach called pulsar timing arrays, simultaneously announced the detection of a gravitational wave background, a low-frequency hum permeating all of space produced by the accumulated gravitational waves from an enormous number of supermassive black hole mergers occurring throughout the history of the universe. The technique works by monitoring the precise timing of pulses, from millisecond pulsars, rapidly rotating neutron stars that emit radio pulses with extraordinary regularity, and looking for correlated variations in arrival times across pulsars, separated by thousands of light-years. Gravitational waves passing through the galaxy stretch and compress the space between the pulsars and Earth, leaving a characteristic pattern in the timing data. In other words, researchers used dead stars scattered across thousands of light-years as a network of microphones to listen to supermassive black holes merging across billions of light-years of cosmic history. The signal they detected is real, consistent across 4 independent collaborations, working on different continents with different instruments, and matches the expected properties of a gravitational wave background from supermassive black hole mergers. TON 618, and objects like it that lived and merged during the most active period of cosmic black hole growth may have contributed to the signal now quietly humming through all of space, a signal we are only just beginning to hear. If we are about to gain the ability to hear the universe through gravitational waves alongside seeing it through light, what will we discover that was completely invisible before? We are living in the rarest moment in the history of astronomy, when the biggest questions are being asked at the same time as the most powerful tools ever built are coming online to answer them. And all of this leads to one final question that TON 618, in the strangest possible way, turns out to be the answer to. There is a tendency, when confronted with objects at cosmological distances, to file them under the category of the impressive but irrelevant. Something 10.4 billion light-years away, something that existed before the Earth existed, something so large it bends the definitions of physical measurement. It is easy to admire it, the way you might admire a mountain range scene from an aircraft window. Vast, real, entirely disconnected from anything that touches your life. TON 618 is not that. It is not a spectacular irrelevance. It sits at the beginning of a chain of physical cause and effect that runs without interruption directly to the existence of everything on this planet, including the person reading these words. The connection is not metaphorical, it is causal. It is written in the chemistry of your cells and the structure of the atmosphere and the orbital mechanics of the solar system. Pull TON 618 and objects like it out of cosmic history, and the universe you are sitting in does not exist. The most direct connection runs through reionization. Before quasars like TON 618 lit up the early universe, space was filled with neutral hydrogen, a fog that absorbed ultraviolet light and prevented it from traveling freely. In that state, the chemistry of life was impossible. Ultraviolet light drives the photochemical reactions that build complex molecules. It sterilizes, yes, but in the right doses and conditions it also initiates the formation of the ozone layer, the energy budget of planetary atmospheres, the photochemical pathways that produce the first organic molecules in interstellar space. All of this depends on a universe that is transparent to radiation. Quasars burned through the fog. They ionized the intergalactic medium and held it ionized, maintaining the transparency of the universe that allowed stellar radiation to travel freely across the distances necessary for chemistry to develop on distant worlds around distant stars. Without that transparency, the chain breaks before it begins. The jets and radiation winds from quasars did something else as well. They physically moved matter. The enormous outflows from active black holes, the same jets that extend tens of thousands of light years from TON 618's poles, carry not just energy but material. They push enriched gas, loaded with the heavy elements processed through stellar nucleosynthesis, out of galaxies and into the intergalactic medium, distributing the raw materials of planetary chemistry across vast distances. The carbon, oxygen, and silicon that eventually assembled into Earth did not stay locked inside the stars that made them. Quasar-driven outflows helped scatter those elements across the cosmic web, seeding the regions where later generations of stars and their planets would form. The raw material of life was in part distributed by the very process that powers TON 618. There is a subtler connection as well, and in some ways it is the most important. Quasar feedback, the regulation of star formation by the radiation and jets of active black holes, acted as a throttle on the rate at which galaxies converted their gas into stars. Without that regulation, galaxies in the early universe might have consumed their gas supply far too rapidly, burning through all available fuel in a burst of star formation that exhausted itself long before the conditions for stable, long-lived planetary systems could develop. A galaxy that converts all its gas into stars in the first 2 billion years has no material left to form a sun-like star 4.5 billion years later, around which a rocky planet might settle into a stable orbit and spend 4 billion years developing life. The pacing mattered. Quasars, by heating and expelling gas and slowing the rate of star formation, helped ensure that galaxies retained enough fuel to keep building new stars across cosmic time, including eventually ours. These are not small or incidental contributions. They are structural. They are part of why the universe has the form it does, and why that form is one capable of producing planets, chemistry, and the kind of stable stellar environment in which biology becomes possible. And yet the universe that made all of this possible is changing. It has been changing for billions of years in a direction that is slow but irreversible. The rate at which new stars form across the universe today is approximately 3% of what it was at its peak, the peak that coincided with the era of TON 618's activity. The great age of cosmic construction is over. Gas that has not yet been locked into stars or black holes is gradually thinning. Galaxies are aging. The star formation rate will continue to decline, and the stars that do form will increasingly be small, dim, long-lived red dwarfs, rather than the massive bright stars that drive the most dramatic chemistry. In the very long run, across timescales measured in trillions of years, the last stars will exhaust their fuel and go dark. What remains will be cold, stellar remnants, black holes, and an expanding ocean of increasingly diffuse radiation. The universe will not end in a dramatic collapse. It will fade slowly and quietly into darkness. We are living right now in the golden age of cosmic light, the era when stars are still abundant, when galaxies are still actively building, when the sky is full of light that will not always be there. This is not a permanent condition of the universe. It is a phase, and we happen to exist within it. The observational window is narrowing in another way too. Because dark energy is accelerating the expansion of the universe, the most distant galaxies are receding from us faster and faster. As time passes, more and more of them will cross beyond our observational horizon, the distance beyond which their light can no longer reach us, even in principle, because the space between us is expanding faster than light can cross it. Today we can observe galaxies billions of light years away, see the cosmic microwave background from the edge of the observable universe, and detect quasars from the first few billion years of cosmic history. We can reconstruct from the light reaching us now a nearly complete picture of cosmic history, from the Big Bang to the present. A civilization existing several trillion years from now, if any such thing were possible, would have none of this. Every galaxy beyond the local group, the small cluster of galaxies gravitationally bound to the Milky Way, will have long since crossed the horizon. The night sky will contain only the merged remnant of the Milky Way and Andromeda and a handful of smaller companions. The cosmic microwave background will have redshifted to wavelengths too long to detect with any conceivable instrument. The evidence that the universe was once full of billions of other galaxies, that it had a beginning, that it has been expanding for nearly 14 billion years, all of that evidence will simply no longer be accessible. A civilization born into that future would have no way of knowing the universe had ever been otherwise. They would look out at their small island of light, surrounded by what appears to be infinite empty darkness, and conclude reasonably but incorrectly that this is all there is and all there ever was. We are not in that situation. We exist at the precise moment in cosmic history when the full scope of the universe's past is still legible in the light reaching us. Every photon from TON 618 that strikes a telescope mirror today is carrying information that will eventually become permanently inaccessible. We are in the middle of a closing window, and the window is one that once shut cannot be reopened. This is what makes the observation of TON 618 something more than an exercise in scientific record-keeping. The light from it is arriving right now, not slowly, not intermittently, but in a continuous stream, photon by photon every second, each one completing a journey that began 10.4 billion years ago. The accretion disk that emitted those photons may no longer exist in the same form. TON 618 itself may have quieted or merged with another black hole or transformed into something our current vocabulary has no name for. We will never know its present state, but its past, preserved perfectly in the light it emitted, carried without aging or distortion across the expanding universe, is available to us now, in this window, during this era, while the instruments exist to catch it and the minds exist to read it. Knowing that we live in the rarest time window in the universe, when the light of all of cosmic history is still visible, what does that change about the way you look up at the night sky tonight? Somewhere out there, 17 billion light years away in real space, TON 618 or whatever it has, still exists in some form we will never know. Its final light is already on its way here. It will take billions of years more to arrive. And when it does, there may be no one here to see it, or there may be no one knows. That is exactly why this matters.